Astronomers estimate there could be 40 billion Earth-sized planets orbiting in the habitable zones of stars within the Milky Way. But the term habitable zone is misleading. It only means a planet sits at the right distance from its star for surface temperatures to allow liquid water. It doesn't guarantee that water is actually there. Liquid water is merely the entry fee. The universe is incredibly hostile, and surviving it requires a planet to navigate a brutal, multi-layered cosmic gauntlet. To find where life can actually survive, we have to map the universe by systematically zooming in and crossing out the dead zones. We have to filter out lethal variables, starting from the massive scale of the entire Milky Way all the way down to a single planetary core. Out of hundreds of billions of planets, how many simultaneous lotteries must a single location win to spark and sustain life? We start with the galactic habitable zone. Like any city, the Milky Way has neighborhoods that are completely incompatible with survival. The galactic center's black hole and dying stars saturate the inner galaxy with sterilizing radiation. The outer spiral arms are safe, but lack heavy metals to form rocky planets. This leaves only a narrow ring of safe real estate in the galactic suburbs. Zooming into that suburban ring, we have to filter the stars themselves. Massive O and B-class stars burn so hot and bright that they exhaust their fuel in just a few million years, long before any complex life can evolve. On the other extreme, M-class red dwarfs can burn for trillions of years, but they regularly erupt with violent solar flares that strip away planetary atmospheres. Plus, any planet close enough to stay warm would be tidally locked, leaving one hemisphere baking in perpetual daylight and the other frozen in eternal night. The surviving candidates are the middle-class stars, stable, long-lived G and K-type stars, much like our Sun. This diagram shows the classic Goldilocks zone, where water neither boils nor freezes. But a planet's path must be perfectly circular. Orbital eccentricity, a highly elliptical orbit, repeatedly flings a planet too close to the star, then too far, creating fatal temperature spikes. Even with a perfect circular orbit, a terrestrial world needs a good Jupiter, a massive gas giant sitting further out in the star system to act as a powerful gravitational shield. Look closely at these dark, bruised impact spots visible in Jupiter's atmosphere. They show how a gas giant actively absorbs comets and asteroids, sweeping the inner solar system clear so rocky planets can develop in peace. A perfect location is useless without a stable path and a planetary bodyguard. This reveals the barren Martian surface. Mars orbits within our Sun's habitable zone, yet remains a dead, dry world with a whisper-thin atmosphere. It failed because it lacks planetary mass. A planet must be heavy enough to generate the gravity required to grip a thick protective atmosphere and keep it from escaping into the vacuum of space. Deep inside, that mass has to stay incredibly hot. The planet needs a violently churning molten iron core. That spinning liquid metal generates a magnetic dynamo, an invisible force field extending out into space that deflects solar winds. Without this protection, the star's harsh radiation peels the atmosphere away, layer by layer, over billions of years. Biological life on the outside of a planet relies entirely on the planet being geologically alive on the inside. Our map has crossed out almost the entire universe. Yet astrobiologists are beginning to discover theoretical loopholes in these rules. Organisms on Earth, known as extremophiles, routinely survive in boiling acid and freezing vacuums. Researchers are also modeling Hycean worlds, hot ocean-covered planets with hydrogen-rich atmospheres that sit outside our standard parameters but might still harbor microbes. While simple microbial life might find ways to cheat the map, complex, multicellular animals remain tightly bound to these strict systemic rules. To achieve that stability, the galactic, stellar, orbital, and geological lotteries must all perfectly overlap. We started with a staggering estimate of 40 billion potentially habitable worlds. The math shows us that a true, sustained equilibrium is vanishingly rare. Astrobiology strips away the idea of Earth as just a standard rock. We are a meticulously balanced oasis floating in a dark, unforgiving void.